8.5 is accounting principles, and I really personally just don't like the way the book is arranged, so I like this first, and we'll go back and do 8.4 next. It's just personal preference. I think it works out better that way. We're going to start back with some kind of middle school ideas. Here's kind of the classic problem of a lunch menu. You're going to pick one of each. You've got a fruit, a main dish, and a drink. And we're going to see how many options you have, how many arrangements of menus you could do. It's going to look like a tree diagram first. So here's the layout. We got 4 fruits to pick from, 3 meats, 3 drinks in the end. So what I could do a tree diagram. I could say apple, and then from apple I could do fish, chicken, or steak. And then from each of those, I've got 3 drink options: soda, juice, and coffee. This is getting kind of annoying, and I've still got a long ways to go. So I really want a faster way to do this at this point in my life. So instead of doing tree diagrams, let's think about what's happening. We're taking each of the fruit choices, and then each one of those branches out to the 3 main course choices. And each one of those branches out to the 3 drink choices. So what's really happening is multiplication here. The number of choices I have for a fruit times how many ways I can pick a main course times how many drinks are available. So I've got 4 fruits, 3 main courses, and 3 drinks. That's 4 times 3, which is 12, times 3 more, which is 36. And you can probably see how this is going to play out in the tree diagram, because just apple alone led to 9 possible outcomes. I've got 4 fruits total to look at. Each one of those is going to have 9 outcomes at the end, so that's 9 times 4 is 36. That's all we're doing. We're just multiplying the number of choices times how many ways it can branch times how many ways it can branch again, and that's how many options we have. So let's build up into a little more complicated stuff. Permutations, combinations. I'm sure you played around with this a little bit in Algebra 2, so we're going to expand on it. So here's the situation. We've got Carl, Sam, Amy, and Phil. They're running for office in the student council. This might seem kind of weird compared to how we do elections here, but it's just to make the problem make sense, that's all. So the winner of the election is going to be president, and the runner-up is going to be vice president. They're not running for 2 separate offices, but again, it's just to make the problem work out nice for us. So how many ways could this happen? How many arrangements are possible? So here's everything that could go down for president and vice president. So maybe Carl gets elected president. Well, there's 3 people that could be vice president under Carl, and so on. That's kind of the idea. So what we're ending up here, if you want to know how many ways are possible, you got 4 people running for president, and then as soon as one person becomes president, there are now 3 people left in the race that could be vice president. So that's 4 times 3 is 12. And that's just going back to the tree diagram idea. But here's your tree diagram laid out, if you want to see it. And that's how it would branch out. But it's 4 times 3. That's what's playing out here. And this is what you would call a permutation. If you have 4 people, and you're choosing an arrangement of 2 of them, but order matters. That's the key here. Order matters. This is how many ways that this could go down. This is how it could happen. So let's change it up a little bit. Let's say that this is now a student council. There's no longer a president and vice president. They're not 2 separate levels of power. They're equal, 2 council members. They have the same amount of authority as one another. So let's see how that changes the outcome. All right, well, here's the same thing I already had, and I just put some abbreviations over there to make it easier. But if they've got the same amount of power, it really doesn't matter if Carl's first and then Sam, or Sam first and then Carl. That's a repeat, because we've already got Carl and Sam together on the council. And the same thing for Carl and Amy. That's the same thing as Amy and Carl. Carl and Phil's the same thing as Phil and Carl. And I'll do this quickly. Sam and Amy is the same as Amy and Sam. Sam and Phil is the same thing as Phil and Sam. And then, what else we got? Amy and Phil is the same thing as Phil and Amy. So I just cut my list in half. There's actually only 6 possibilities here, because I've divided out any repeats, since order doesn't matter. Now hopefully that kind of makes sense, that order mattering would have more outcomes, because we really have to pay attention to who's first, who's second, whereas if order doesn't matter, we've got rearrangements that are the same thing, and we can divide or just take those out of the final answer. Now there's an organized way of how you do this, and I'm going to get to that in just a second. But for right now, let's just count them, and there's 6 possible arrangements. That came from the original 12 arrangements that I laid out, but we had to take out any repeats. And right now, that's all I want you to think about. For combinations, you're taking out any repeats you had from the permutation when order no longer matters. So recap, permutation, and there's a reason I did president and council. Permutation for president, order matters. Combination for council, order doesn't matter. So keep that in mind. Permutation, order matters, more outcomes. Combination, order doesn't matter, less outcomes. You got repeats you can take out. Let's talk about how we come up with this. So permutation and combination formulas. Let's actually come up with an empirical way to get a formula for these. And I'll be honest, when I used to do this stuff in high school and even in college, the formulas just looked really bizarre and I never quite understood them. So we'll try to give this to you in an example format. So hopefully the formulas make sense and you don't just see they seem magic to me. So I'm going to try to make them less magical and make them make sense to you, hopefully. All right, a permutation. Let's suppose we've got 10 runners in a race and the top 4 are going to get a medal. All right, and I'm talking 4 different medals: gold, silver, bronze, and I don't know, participation trophy. So order matters. They want whoever comes in first, they want to get that first place medal. Order matters. So let's think about how this could go down. There are 4 positions: first, second, third, and fourth place. And we can certainly do a tree diagram, but I'm going to try to simplify it into a math problem and avoid all that drawing because that's going to get pretty bulky. So if there's 10 people running the race, taking ability out of the equation, just thinking pure, everybody had an equal chance. How many people could come in first place? Well, if all 10 people are running, at that time, anyone could still win. So there are 10 people who could finish first. As soon as one person crosses that line, you got 9 people still running the race. So how many of those could come in second? Well, there's 9 different people who could come in second. So now we're up to 10 times 9. Now if 2 people cross the finish line, there's now a pack of 8 people running the race, going for third. So out of those, there's 8 different ways those people could cross the line. And eventually, of the rest of the pack, 7 people, and 1 person will come in fourth. So 10 times 9 times 8 times 7, that is your final answer. And I'm actually not going to multiply it out, because that's really all I want you to see. So before I introduce symbols and create a formula, let's try to make this a little more mathematical. Let's go come up quite a bit of factorials. Now, hopefully you remember about factorials. If you had a 4 factorial, that would be 4 times 3 times 2 times 1. There's every number, starting with that number, times the number below it, times the number below that, all the way to 1, and you stop at 1. Because if you put in 0 there, it becomes 0. It doesn't really make sense. So you stop at 1. And that's what a factorial is. Now, what we got going on here is sort of the factorial pattern, but it stops at 7. So here's another way to think about this. You've got 10 times 9 times 8 times 7. And I'm going to say dot, dot, dot for now, because what I'm really doing is I'm dividing out everything from 6 down. I mean, don't worry too much about why I know that. Just think about the fact that that's what this would be. I mean, that would be times 6 times 5 and onward. All that stuff is the same, so it divides out, and you don't see it. So here's the formula way to look at it. If n is the number of elements possible, that's the 10 people running the race, and r is the number chosen, which that's the 4 people who finished the race. So let's think about how this plays out. It's going to be 10 factorial on top divided by 6 factorial on the bottom. Well, how does 6 compare to the original 10 when you put 4 in there? 6 is 10 minus 4. So again, not so much worried about how I definitely came up with that but just seeing that it does work is where I would kind of settle right now. And seeing that this is 10 factorial divided by 6 factorial. And the way we got 6, at least the way we could come up with it, is 10 people run the race minus the 4 that finished. I guess the 6 people who didn't finish, could think of it that way. All right, so keep that in mind. N is, again, the number of people run the race. R is how many are chosen. And that is your permutation formula. So the large number on top, and then that large number minus how many people are chosen on the bottom, both of those factorial, that's how you calculate a permutation. For combinations, I'm going to start with the same idea, the same race, 10 runners, 4 people finished. But we're going to change it up a little bit so that order no longer matters. So instead of these fancy medals that we all want to get first place for, it's just going to be the top 4 go on to states. And it really doesn't matter as far as who's going to states, who came in first, second, third, fourth. It's just those 4 people go to states. And they're all back on equal footing at that point. So in this case, it's a combination because the order doesn't matter. Now, if you're a competitor, you know order always matters. But in this, for the sake of the math, order is not important because it's all about how can a team of 4 be sent to states. And it doesn't really matter what order those 4 people are in, just a selection of 4 people. So let's think about kind of how this might go down. We already know that the permutation was 10 times 9 times 8 times 7. So we need to divide out our repeats here. And let's just say that one possible way, and I'm just going to say A, B, C, D. Let's say one possible way 4 people finished was that arrangement. Let's just say that's their initials. Somebody's name start with A, B, C, and D. Well, if order doesn't matter, then A, C, B, D would be the same team, and A, D, B, C would be the same team. Now, what I'm saying is if this is the order the 4 people finished in, but when it's just coming down to a team of those 4 people going to states, the order they finished in really isn't important. It's just that those were the top 4 finishers. So if you kind of think about how this might play out, it's another permutation because if there's four spots, then someone gets the first spot. Let me make 4 spots here. If someone gets the first spot, there's 3 people left that could get the next one, 2 people left that could get the next one, and then ultimately somebody comes in last. But instead of worrying about that as far as order, it's more about the arrangements. There are 4 times 3, which is 12 times 2, 24 different ways that we could arrange these 4 people. Now, if you thought about making a list of all the ways these 10 people could finish, that's going to be a really lengthy tree diagram, but you would see this arrangement of A, B, C, and D 24 times and have to divide those repeats out or scratch them out. We don't want to go through that whole process. We just want this idea that of the repeats, if there's 4 people finishing, then there's 4 factorial repeats. And this is why, because for any group of 4, you can arrange it in 4 factorial ways. So maybe instead of thinking about order, it was more about how many ways a team of 4 could be arranged, how many ways they could finish the race and still that team of 4. So that's how that's going to play out. If we think about this compared to our original formula, or how we did the math a few minutes ago, so again, it was 10 times 9 times 8 times 7. That was how many possible permutations where order matter could happen. But now we're additionally dividing out these 4 factorial repeats. So all I'm doing is a scaled up version of this. If I have my original tree diagram, and I'm going here scratching out all my repeats, there's just a lot more repeats to this problem with the racers, and that's why I'm trying to come up with a better way to do it. I don't want to list out a tree diagram. It's going to take way too much paper, way too much time. So let's try to generalize it to a formula. If I know that the way I got this permutation was taking the 10 racers and dividing by the number of people who didn't finish, the 10 minus the 4 chosen, and now additionally I'm dividing, again, this is how I got the top number, but I'm also dividing out these arrangements for how any group of 4 could be different, how they could be arranged as repeats. Now it's starting to look like that. So just again to reiterate, you're dividing out your repeats, there's 4 factorial ways that a group of 4 people could all be arranged, and it would still be that same team of 4 people going on states. So if you put it into your formula, there's your permutation formula right there, and we're dividing out these repeats. So it's the number of people in the race divided by the number of people minus how many were chosen, 10 minus 6 in this case, 10 minus 4, sorry. And then additionally dividing out your repeats, so 4 factorial, the number chosen factorial. Distinguishable permutations is sort of a weird idea. Hopefully I can make this make sense to you. Not just ask me about it, we can keep talking about more problems like this. But it's how I could arrange the letters in a word and be able to tell the difference. So I'm going to try an approach that seems to work well, and that's with color coding. If you have trouble seeing the colors, hopefully when you see me move stuff around, you get the idea and you see why it would work. So I'm asking you, how many distinguishable ways can the word banana be written? So it's kind of a weird idea because it's the word banana, or at least the letters in that word. But imagine that these are Scrabble tiles, and my 3-year-old has colored on them. So each Scrabble tile is a different color. Well, now if I rearrange the letters in that word, you can noticeably tell the difference, or you can distinguish a different arrangement, and that's really what we're going for. So that's why I colored these in. So here's the word banana. If I take a blue A next, and then the black A, the blue N, and the red A. So all I changed was I switched these 2 A's around. And now, I mean, it's distinguishable. It's banana, but it's written, you can tell that I did something. And I can keep doing different ways of changing the letters around. And it's distinguishable because you can tell that I've switched some things around, but it's still the same word. So just seeing it in black and white, it's kind of hard to get the idea, but imagine they're Scrabble tiles and I'm rearranging the letters. I'm still spelling the same word, but I'm putting the letters in a different arrangement. So the letters in the word banana, well, there's 6 tiles. So if you think about, let's just say I magically had these 6 letters, that, I happened to spill this, but that's just, I had those in a bag and I started just pulling one out blindfolded at a time. Well, there's 6 letters that could go first, 5 that could go next. Once I've placed 2 tiles, there's 4 in the bag, then 3 in the bag, and so on. Which you can do a tree diagram as well. But now I'm looking at all the ways I can scramble these letters around. Not necessarily spelling the word banana, but just scrambling these letters around. That's how many ways it can be done. Right? That's a permutation. If you really want to get down to it, it's a permutation where you choose all the letters. I don't think you need to get that detailed here, but that's your permutation. So 6 factorial is what that comes out to be. But if you think about what's going to be repeated, well, these 3 A's, actually let me start with the ends, it's probably a little simpler. There's 2 ways the ends could be swapped around. So for any of these arrangements of these letters, you could swap the ends, and if they're black and white, you can't tell, but if you color them, you can tell that you switched them around. So that divides everything in half right there. And then there's going to be more things I could divide up, because these A's, well, there's 3 A's, so there's, I could think of it this way. If I had 3 of these A's in the bag, for the first spot, there's 3 possibilities. The next spot, there's 2 left. If I'm just pulling one out at a time. So that's 3 factorial, or 6 ways. So hopefully, I don't know if it's making a full amount of sense. I hope it's kind of giving you an idea of how it's working out. But you have these repeats because if you could distinguish one letter from an A from another A, you can see that the order changed. And that's really what it's getting down to, is how you could change the order of these letters. So what it comes down to, and I'm going to go ahead and say factorial, because there were, with 2 letters, there were 2 ways, but that's 2 factorial is still 2. So that's what's happening right there. It's all the ways you could arrange these 6 letters, where it's not necessarily spelling a word. But for any of those arrangements, we could swap the ends, and we could swap the a's around. And there would be 2 factorial ways to swap the ends, which is just 2. And 3 factorial ways to swap the a's around, which that would be 6 different ways to arrange those a's. And you really couldn't tell that that's a different word unless, again, they were colored or it's some way to distinguish one letter from another. So that's what's going on. That's how this works out. And here's the formula. Here's the way the book's going to write it, so I'll run through real quick. You probably don't need to memorize all this stuff, but I just want to make sure you do see the math language and think about it. So if a set contains n elements, in this case, that's the 6 letters in the word banana. That's my 6 I'm coming up with you. So 6 elements for banana, and it's made up of different distinguishable letters. A B, N2, that'd be like an A. N3 could be like the N. So this 6-letter word is made up of some B's, some A's, some N's. That's the idea. And the way you get your formula is you take however many letters you have in the beginning, so if it's 10-letter words, 10 factorial, and you divide it by the number of repeated letters. So if there's 3 A's, 3 factorial, 2 N's, 2 factorial. And if you want to do any single letters, you can. There was a B, so 1 factorial can go in there, but you don't really have to include those because 1 factorial is still 1. Usually you just take the repeated letters and those divide out the number factorial, and that's how you get it. So if we need to talk about that one more, we can. I know that's kind of a tricky one to grasp. Once you get the idea, it's not too bad. It's just kind of a weird one to really wrap your head around at the beginning, I think. A couple technical details. When you encounter the word and, that's the tree diagram. Pick this drink and this main course and this fruit. So that's multiplication going on. Or, I always like to think of it as like a bonus chance. So I'm rolling the dice, and if I get an even number or I get a 5, I win. So when you see the word or, just remember to add things together. Finally is understanding 0 factorial and why in the world this is true. It seems really bizarre. It seems like 0 factorial should probably just be 0. I've done this approach for several things this year, and I think it's one of the best ways to approach ideas like this that don't make much sense. Start off with some things that do make sense, and then create a pattern that narrows in on what you're looking for here. So I've just got some things that do make sense with factorials, and I'm going to extend it on down and just kind of see what conclusions I can come to. So I'm going to fill in things that make sense first. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. Now let's think about a pattern to fill in the rest of this. So what happens if I go from 24 to get to 6? Right, what are we doing? Well, sometimes going forward might help. We took 6 and multiplied by 4 to get 24. So we can divide by 4, and that's how you go from 24 to 6. Now to get from 2 to 3 factorial, you multiply by 3, so to undo it, we would divide by 3. To go from 2 to 1, we're dividing by 2. So if we follow this pattern, that means we should probably divide by 1 next. So 1 divided by 1 is 1. And there we go. I mean, that's what it's coming out to be. And if we follow this pattern, you would divide by 0 next. Well, 1 divided by 0 is not defined. I guess you could say infinity, but I think this is a point where undefined fits the situation better because you can't really have a negative factorial. Now, hopefully that puts it in perspective. If you continue, like we were doing 4 factorial and we continued until we got to 0, 4 times 3 times 2 times 1 times 0, well, you'd never have anything. It would always be 0. So that wouldn't make much sense. And if you allowed yourself to get to the negatives, where would that stop? Would you continue the negatives until you got to negative infinity? Because then you wouldn't really have an answer either. So it only makes sense logically when you think about how you're counting arrangements for countable objects. It kind of only makes sense to stop at 1. But if you follow the pattern, that's where this would have to check out. And then finally, here's an example that might put it into the formulas we were already working with and show you why it has to be what it is. So out of 20 items, suppose I choose none. I walk up to a booth at an auction or something, and there's 20 things laying there, and I decide I don't want any of them. So how many ways can that happen? When you think about that, there's one way. There's one way I can walk up to a bunch of objects and say, no, I don't want any of them. I mean, there's one way I walk away with nothing. So that answer should be 1. 20 choose 0, I should be getting 1. You put it in the formula, it's 20 factorial over 20 factorial times 0. Well, that divides out to 1. The only way this checks out is if this piece here is 1. We could think of it as 0 factorial being a variable like x, like what in the world is that? But knowing that this should be one way in the end, and then you solve and you see that 0 factorial has to be 1. So a couple ways to think about it, but in the end, make sure you remember the 0 factorial, weird or not, it is 1.